Hello and welcome. Today we're going to embark on a journey through the world of numbers and language. By the end of this lesson, you will be able to identify and differentiate between various types of numbers, including natural numbers, integers, rational numbers, and irrational numbers. We'll start with the most fundamental set of numbers. These are the natural numbers, which we denote with the capital letter N. Think about when you first learned to count. 1, 2, 3, 4. These are often called counting numbers. When we include 0, we get the set of natural numbers. So, the set of natural numbers, N, is represented as the list of numbers starting from 0 and continuing indefinitely. But what about numbers below 0, like on a cold day? For that, we need a larger set. This brings us to the integers, represented by the letter Z. Integers include all the natural numbers, their negative counterparts, and 0. So if the temperature is 4 degrees and drops by 6 degrees, it becomes -2. That's an integer. The set of integers, Z, includes all positive and negative whole numbers, along with 0. Notice that every natural number is also an integer, so the set N is a subset of the set Z. Now, what about fractions or parts of a whole, like 3½ For this, we use rational numbers, denoted by the letter Q. A rational number is any number that can be expressed as a fraction, where the top and bottom are both integers, and the bottom number, the denominator, is not 0. This includes all integers, because any integer can be written as a fraction over 1. For example, 1/2, -3/4, the number 7, and even terminating decimals like 0.2 are all rational numbers, because they can be written as fractions. But not all numbers can be written this way. Numbers that cannot be expressed as a simple fraction are called irrational numbers. These numbers have decimal representations that go on forever without repeating. Let's look at a classic example. Consider a right-angled triangle where the two shorter sides both have a length of 1. Using Pythagoras' theorem, the length of the hypotenuse, the longest side, is the square root of 2. The value of the square root of 2 is a decimal that continues infinitely with no repeating pattern. This makes it an irrational number. Another famous irrational number is pi. When we combine all the rational numbers and all the irrational numbers, we get the set of real numbers, which we call R. So we've seen how our number system is built up from simple counting numbers to a vast set that includes integers, fractions, and even numbers that can't be written as fractions. We've successfully identified natural, integer, rational, and irrational numbers. In this next section, our goal is to learn how to identify prime numbers and how to break down other numbers into their essential components, known as prime factors. First, let's define what a factor is. A factor of a number is any number that divides into it exactly, with no remainder. For example, the factors of 12 are 1, 2, 3, 4, 6, and 12, because each of these numbers can divide 12 without leaving a remainder. Now, some numbers have very few factors. These are called prime numbers. A prime number is a whole number greater than 1 whose only factors are 1 and itself. It's a very important definition. A prime number has exactly 2 factors, 1 and the number itself. For instance, 7 is a prime number because only 1 and 7 divide into it. The number 2 is the first prime number, and it's also the only even prime number. It's important to note that the number 1 is not considered a prime number. A great way to find prime numbers is using a method called the sieve of Eratosthenes. Let's try it for numbers up to 100. First, we write out all the numbers from 1 to 100. We start by crossing out 1, as it's not prime. Next, we circle 2, our first prime, and cross out all of its multiples. This eliminates all the even numbers. The next available number is 3. We circle it and cross out all of its multiples. We continue this process. We circle 5 and cross out its multiples, then circle 7 and cross out its multiples. The numbers that are left, that haven't been crossed out, are all the prime numbers less than 100. Now that we know what prime numbers are, we can talk about prime factors. Any whole number that is not prime can be written as a product of prime numbers. These are its prime factors. Let's find the prime factors of 18. A simple way is to divide by the smallest prime numbers in order. We start with 18. The smallest prime that divides it is 2. 18 divided by 2 is 9. Now we look at 9. The smallest prime that divides it is 3. 9 divided by 3 is 3. Finally, 3 divided by 3 is 1. Once we reach 1, we stop. The prime factors are the numbers on the left, so 18 can be expressed as the product 2 times 3 times 3, or, more concisely, 2 times 3 squared. Let's do another one, say 75. For 75, the smallest prime factor is 3, which gives us 25. The smallest prime factor of 25 is 5, which gives us 5. And 5 divided by 5 is 1. Therefore, the prime factorization of 75 is 3 times 5 times 5, or 3 times 5 squared. This process of breaking a number down into its prime factors is a fundamental skill in number theory. In this scene, we will build on our knowledge of factors and learn to find the highest common factor and the lowest common multiple of numbers. These are very useful concepts, especially when working with fractions. Let's begin with the highest common factor, or HCF. The HCF of 2 or more numbers is the largest number that is a factor of all of them. In other words, it's the biggest number that divides into all the given numbers without a remainder. Let's find the HCF of 12 and 18. First, we list all the factors of 12. These are 1, 2, 3, 4, 6, and 12. Next, we list all the factors of 18. These are 1, 2, 3, 6, 9, and 18. Now, we look for the factors that appear in both lists. These are the common factors, 1, 2, 3, and 6. The highest of these common factors is 6, so the HCF of 12 and 18 is 6. This means 6 is the largest number that divides both 12 and 18. Now let's move on to the other concept. This is the lowest common multiple, or LCM. A multiple of a number is what you get when you multiply it by an integer. The LCM of 2 or more numbers is the smallest number that is a multiple of all of them. Let's find the LCM of 6 and 10. First, we list the first few multiples of 6 to 6, 12, 18, 24, 30, and so on. Next, we list the first few multiples of 10, 10, 20, 30, 40, and so on. We look for the first number that appears in both lists. In this case, it's 30. So, the LCM of 6 and 10 is 30. This means 30 is the smallest positive number that is divisible by both 6 and 10. To recap, the HCF is about finding the largest common factor, while the LCM is about finding the smallest common multiple. We've now learned how to calculate both. Welcome back. In this scene, we're going to explore powers and roots, focusing specifically on squares and square roots. By the end, you'll be able to calculate the square of a number and find its square root. Let's start with square numbers. A square number is the result of multiplying a whole number by itself. For example, 3 times 3 is 9, so 9 is a square number. We use a special notation for this called index notation. 4 times 4 is written as 4 with a small 2 above it, which we read as 4 squared. The result is 16. This idea is directly related to the area of a square. Let's look at a worked example with decimals. Imagine a square with sides of length 1.1 units. We want to find its area, which is 1.1 squared. We can visualize this by breaking the square down. We have a large 1 by 1 square, which we'll call A. We have 2 thin rectangles, B, that are 1 by 0.1. And we have a tiny square, C, that is 0.1 by 0.1. The area of A is 1. The area of each B is 0.1. And the area of C is 0.01. Adding these all together, the total area is 1 plus 0.1 plus 0.1 plus 0.01, which equals 1.21 square units. So 1.1 squared is 1.21. Now let's look at the inverse operation. This is called finding the square root. The square root of a number is a value that, when multiplied by itself, gives the original number. It's like asking what number squared gives me this. For example, the square root of 16 is 4, because 4 times 4 is 16. We use this radical symbol to denote the square root. There's an important detail here. Notice that negative 4 times negative 4 also equals 16. So technically, 16 has 2 square roots, positive 4 and negative 4. However, by mathematical convention, when we write the square root symbol, we are referring only to the positive root, which is called the principal square root. So the square root of 16 is 4. Finally, what about the square root of a negative number, like minus 16? Since squaring any real number, positive or negative, results in a positive number, there is no real number that is the square root of minus 16. So we've now covered how to square numbers and how to find their principal square roots, understanding the important conventions along the way. Now that we've mastered squares and square roots, let's take it one dimension further. In this scene, our objective is to understand and calculate cubes and cube roots. Let's begin with cubes of numbers. A cube number is the result of multiplying a whole number by itself 3 times. This concept is related to the volume of a cube. For instance, a cube with side length 2 units occupies a space of 2 times 2 times 2, which is 8 cubic units. Just like with squares, we use index notation. 4 times 4 times 4 is written as 4 with a small 3, which we read as 4 cubed. The result is 64. So cubing a number means raising it to the power of 3. It's a straightforward multiplication, just repeated twice. And just as square roots are the inverse of squaring, cube roots are the inverse of cubing. Let's talk about cube roots. The cube root of a number is the value that, when cubed, gives the original number. The symbol is similar to the square root symbol, but with a small 3 in the nook. For example, the cube root of 64 is 4, because 4 cubed is 64. We are asking, what number multiplied by itself 3 times gives me 64? Now here's a key difference from square roots. Remember how we couldn't take the square root of a negative number? Let's consider the cube root of negative 64. Is there a number that, when multiplied by itself 3 times, gives a negative result? Let's try minus 4. Negative 4 times negative 4 is positive 16. Then positive 16 times negative 4 is negative 64. It works! So, the cube root of negative 64 is negative 4. Unlike square roots, you can take the cube root of a negative number and the result will be negative. To summarize, we've learned that cubing a number means raising it to the power of 3, and finding the cube root is the inverse operation. We've also seen the important distinction that we can find the real cube root of any number, positive or negative. In our final scene, we'll focus on a practical application of our number systems, directed numbers. Our goal is to use the concept of positive and negative numbers to solve real-world problems, like changes in temperature. Directed numbers are simply numbers that have a direction, positive or negative. A number line or a thermometer is a perfect way to visualize this. 0 is the reference point. Numbers to the right or above 0 are positive. Numbers to the left or below 0 are negative. Let's use this thermometer to work through an example. Imagine the temperature at 4 in the morning was minus 3 degrees Celsius. By 9 in the morning, the temperature had risen by 8 degrees Celsius. What is the new temperature? We start at minus 3 on our thermometer. A rise in temperature means we move to the right in the positive direction. We need to move 8 units. Moving 3 units gets us to 0. We still have 5 more units to go. Moving 5 more units to the right lands us on positive 5. So the new temperature is 5 degrees Celsius. We can write this as an equation. Minus 3 plus 8 equals 5. Let's try another one. Suppose the temperature was minus 7 degrees and it falls by 11 degrees. This time, we start at minus 7. A fall in temperature means we move to the left, in the negative direction. We move 11 units to the left from minus 7. Moving 11 units to the left from minus 7 brings us to minus 18. So the new temperature is minus 18 degrees Celsius. This concept isn't just for temperature. It applies to bank balances, where a deposit is positive and a withdrawal is negative. It applies to elevation, where sea level is 0, mountains are positive, and the ocean floor is negative. Let's consider one last problem. The highest temperature recorded in Libya was 58 degrees Celsius. The lowest in Antarctica was minus 88 degrees Celsius. What is the temperature difference? To find the difference, we subtract the lowest temperature from the highest temperature. That's 58 minus negative 88. Remember that subtracting a negative number is the same as adding its positive counterpart. So, 58 plus 88 gives us a total difference of 146 degrees Celsius. That's a huge range. Today, we have journeyed through the fundamental building blocks of mathematics, from the simplest counting numbers to the complexities of irrationals, primes, powers, and directed numbers. Understanding this language of numbers is the key to unlocking more advanced mathematical concepts.